Hey everyone, welcome to our channel. Today, we will dive into an end-to-end machine learning workflow in NIME. We will build and compare three machine learning models, logistic regression, random forest, and decision tree, and save the results to Excel. So, let's jump right into it.
First part, data preparation. Step 1, reading the data with CSV reader. Our first step is bring the data into NIME using the CSV reader node. This is where everything begins. Whether we are working with customer churn data, credit card fraud detection, patient medical records or any other data set, the CSV reader imports it in a structured format read for analysis. It's a flexible starting point that lets us load raw data directly into our workflow. Step 2, handling missing values. Real world data often comes with gaps or inconsistent. That's where the missing value node comes in. NIME provides multiple strategies to deal with the missing data. We can replace missing values with our default or estimate value. Remove rows or columns that contain them. Though here we are remove the rows containing missing values. This step is very crucial for ensuring our downstream analysis and machine learning models function correctly without being shaked or interrupted by null values. Step 3. Filtering unnecessary columns. Next, we use the column filter node to the streamline our dataset. Often, dataset includes columns like customer IDs, timestamps or other metadata that don't contribute to the analysis or model performance. By removing this, we reduce noises and make our dataset are more focused and manageable. Step 4. Normalizing numeric features. Now we move on the normalization, a key processing step, especially when using algorithms that are sensitive to scale of input features such as logistic regression or neural networks. The normalizer transfer numeric columns to a common scale, ensuring that no single feature disproportionately influences the model just because of its scale. Step 5. Converting types and one-hot encoding. Finally, we address categorical data. Some numeric columns might actually represent categories. In such cases, we convert these from numbers to string using the numbers to string node. Then, to prepare categorical features for machine learning algorithms, we use the one-to-many node. This node performs one-hot encoding, turning each category into its own binary column. This makes the data fully numeric and suitable for most ML algorithms.
Our second part is sampling and balancing. First step is adding custom logic with rule engine. In some cases, we might want to enrich our data with custom rules before moving on to the modeling. This is where the rule engine node comes into play. With this node, we can create new columns or flag specific rows based on conditions we define. For example, we might create a new category for high risk customers if their spending exceeds a certain threshold, or tag certain rows based on location, transaction type, or any other logic relevant to our analysis. While this step isn't always necessary, it's a powerful way to add domain specific insights directly into your dataset. With SMART, a critical step is preparing many real world datasets is addressing class imbalance. Often, the events we are trying to predict, such as fraud cases, disease diagnosis, or customer churn, are relevantly rare compared to the majority class. To tackle this, we use SMART, which stands for Synthetic Minority Oversampling Technique. Unlike simple oversampling, which duplicates existing minority class examples, SMART creates entirely new synthetic samples. These new examples are generated by interpolating between existing minority class instances, helping to enrich the dataset without simply repeating the data. Balancing the classes in this way helps our machine learning models learn patterns more effectively, improving their ability to correctly predict rare but important outcomes. Our third part is model training. Step 1, splitting the data with partitioning. Before we build any models, we need to separate our data into two parts, one for training and one for testing. This is done using the partitioning node. The idea is simple but essential. We train our models on one portion of the data and evaluate their performance on a different portion that the models have not seen before. This helps us test how well our models generalize to new unseen data. Typically, we might split the data 70 by 30 or 80 by 20 between training and testing, but the exact split can be adjusted depending on the use case. Step 2. Training the models with learner nodes. With our training data ready, we built three different models, each using its own dedicated learner node. First, Logistic Regression Learner. This is a classic statistical model often used for binary classical problems, such as predicting whether a passenger will survive or not. It's simple, interpretable, and works well when the relationship between variables is linear. Second, Random Forest Learner, a more advanced machine learning model. Random Forest builds multiple decision trees and combines their result. It handles complex relationships in the data and the trains to perform well on a variety of tasks. Last, Decision Tree Learner. The model builds a single decision tree, splitting the data into branches based on features values. It's easy to visualize and interpret, but can sometimes overfit the training data if not properly tuned. All three models are trained on exactly the same database, allowing us to later compare their performance and understand which algorithm works best for our specific problem.
Now, the fourth part is prediction and evaluation. Step 1, making predictions with the models. Now that our models are trained, it's time to see how they perform. We feed the test data into each of the following corresponding nodes: logistic regression predictor, random forest predictor, and decision tree predictor. Each predictor applies its trained model to the test data, generating predictions on whether each instance belongs to the target class. This step gives us the output from all the three models and ready for the evaluation. Step 2, evaluating model performance with scorer nodes. To understand how well each model performs, we use the scorer nodes. These nodes calculate each important evaluation metric such as accuracy, precision, recall, F1 score. Accuracy, how often the model predicts correctly. Precision, how many of the positive predictions are actually correct. Recall, how many actual positives were correctly identified. F1 score, the balance between the precisions and recalls, and many others. These matrices gives us a detailed look at each model's strengths, weaknesses, helping to choose the best one for the task at hand. Step 3, visualizing model performance with the ROC curve. Beyond numbers, we also want a visual comparison. The ROC curve plots the true positive rate against the false positive rate at various threshold settings. A model that curves closer to the top left corner of the plot performs better at distinguishing between classes. By plotting the ROC curves of all three models together, we can visually assess which one has the best classification power.
Fifth part is exporting result. Step 1. Combining the result with a concatenate nodes. Once we have scored each model, we use concatenate nodes to bring all the result into a single unfitted table. This makes it easy to compare prediction side by side, see where models agree or disagree, and predict the result for export. Step 2. Saving the result with Excel writer. Finally, we make our work shareable. Using the Excel writer node, we export the combined result to an Excel file. This allows us to easily review the outputs in a familiar format or include them in presentation and reports.
And that's it. We have just walked through a complete machine learning workflow in 9. Reading and cleaning your data, balancing your dataset, training multiple machine learning models, evaluating their performance, and exporting your results for sharing or reporting. The beauty of 9 is its flexibility. You can extend this workflow in countless ways. Add neural networks, try ensemble learning techniques, explore advanced features, engineering, or automate the process for continuous improvement. Share your thoughts about the video in the comment section. Thanks for watching.